Good noon, everyone. I am Semin Kim from Korea Research Institute of Chemical Technology, Center for Bio-Based Chemistry. First of all, I'm very sorry that I cannot do presentation on site due to some problems related with COVID-19 issue. I'm going to introduce one of our research theme self-healing materials titled An Innovative Time Temperature Indicator for Food Safety Based on Self-Healing Nanofiber. I prepared this presentation in a casual tone, not an intensive one. Please listen lightly. Nowadays, there are lots of easy-to-cook packages called meal kits on the market. And many companies are eager to deliver fresh food materials because many people have become interested in cooking due to the influence of the media like TV shows and YouTube. This phenomenon is also affected by the worldwide crisis COVID-19. When it became difficult to go to the restaurant, people began to cook for themselves. This graphic shows the online mobile shopping trends of Korean in February this year. Food, beverage, and delivery services that can account for more than 27% of the total consumption. These represent an increase compared to the last year. This kind of social phenomenon continues, and the importance of the cold chain supply system has increased. Microorganisms that cause food poisoning are classified as mesophores that multiply well in room temperature to body temperature like environment. We call this temperature range a danger zone. As I mentioned earlier, the frequency of online shopping for food and beverage has increased, and we could receive the items through the delivery system. But some problems can arise in this process. Our items might be left outside or the air conditioner of the system might do not work well. Then the food goes bad easily. Customers cannot know the details in the delivering step. To resolve these kind of problems, we need time temperature indicators, in abbreviation TTI. Of course, there are TTIs on the market already. Typical TTI has two mechanisms like this. One is diffusion type and the other is chemical reaction type. The first one uses temperature sensitive dyes and permeable membrane layer. It has disadvantages of low sensitivity to temperature and inflexible characteristics. And also, it is weak for external shock. The dye in the module could be leaked outside. The second one is composed of small molecules, for example, polymerizable monomers or enzyme like that. They can also spill out of the TTI. It is not only harmful for food and human bodies, but also expensive. So we wanted to find a breakthrough beyond these problems. Our TTI is based on the self-healing polymer nanofiber fabricated by the electrospinning method. The polymer solution is composed of the self-healing TPU and binary solvent. Here, the solvent is also much important factor. One of the components is a good solvent for the polymer and the other is a volatile solvent as an assistant to solidification of fibers. To fabricate a well-stacked nanofiber nanoven, we optimize the moiety of polymer in the solution and the ratio of co-solvents. The electrospun nanofiber was collected on the water bath. In this process, the residual hydrophilic solvent was removed by water. If we didn't carry out the washing step, the nanoven structure could be broken easily due to the dissolving problem, not only self-healing effect. Then, the nanofiber mat was used to make the TTI with cover films. Self-healing of our product begins at the metathesis of disulfide groups and hydrogen bonding of the uracil functional group. These act as a driving force of the self-healing characteristics. Based on the intra and intermolecular attraction, the opaque TTI changes to the transparent film. As I said that our TTI is based on the nanofiber. It means that the material has a high specific surface area and a number of points of contact. This is a strong point for the self-healing effect. The much more important point of our TTI is the irreversible characteristic. When we apply this TTI for food packages, we can recognize the thermal exposure history. At room temperature, the transmittance changes in short time. But there are less changes at 2 and minus 20 degrees of Celsius as a storage temperature. And also, we cannot observe the diminishing transmittance even in minus 20 degrees of Celsius. The thickness of nanofiber mat is very important factor too. When we conduct the electrospinning longer time, the nanofiber mat has much higher thickness. The initial absorbance of the mat is proportional to the thickness of it, and the time the changing opaque to transparent is also affected by the thickness. As one of the factors which can control self-healing time, we could adjust the optimal level of the deposition time. Moreover, we could control the rate of self-healing by changing the synthesizing conditions, equivalent of the components, reaction time, reaction temperature, and so on. We expect that to be able to apply this TTI for various product lines, frozen food, chilled food, even for vaccine like that. I'm sorry that I cannot explain this in detail because this technology was transferred to a Korean company. As a result, the key points to determine the self-healing time of our TTI are thickness of the nanofiber, thickness of the electrospin mat, and synthesizing conditions. Here, all the variables are very critical. The performance of the TTI is up to the harmony of the variables. I'm gonna show a short interesting video. The initially opaque white TTI turned transparent after 48 hours, showing a question mark in the backplate. The self-healing rate depends on the storage temperature. The sample which is used in this video takes 2 days to change at 10 degrees of Celsius. Okay, let's see the SEM images on the right side. In the first row, there are similar images of the nanofiber. For this case, TTI was stored at minus 20 degrees of Celsius. During long time, less transition of morphology was observed. This means that self-healing didn't appear for that sample. But in the second row, after 1 or 2 days, the porous structure was broken down. And in the last row, the collapse of the nanostructure was accelerated because the TTI was exposed to higher temperature. The shown sample was fabricated for the chilled food. The chilled food had to be stored below 4 degrees of Celsius. The food stored under warm environment may cause food poisoning to people. Our TTI dictates such risks. In short, we develop a safe TTI that can also be applied to food packaging based on the self-healing nanofiber. This item has irreversible, flexible characteristics, and there is no concern about chemical leakages. We already transferred this technology to the company in Korea, This technology will be used in a variety of packaging. Thank you for your kind attention. If you have more questions in detail, please contact us. Our email address is here.